Physics 101, work and energy homework, question number 10. We have a statue. It is sliding down a ramp. The curator is holding it up, applying a force so that it won't slide down. It's not going to accelerate. So the acceleration is 0. It's going to slide smoothly down the ramp. The velocity is going to be going down the ramp, and we're calling the down the ramp positive x direction. All right. So we have some forces acting on this. Ultimately, we're going to be finding the work done. The work done by gravity, the work done by friction, the work done by the curator. We're also going to find the work done by the normal force. That's also asked for, but it got cut off when I took screen capture of the problem. Okay, so forces that are acting on the box, the crate with the statue in it. There's a gravitational force straight down, Fg. There's a normal force that's perpendicular to the surface of the ring. There's an applied force from the curator, so we'll call it F curator. And then there's going to be a frictional force as well. F sub k, its coefficient. Static or kinetic friction, it is sliding, so it's F sub k. We're given some information. We know the mass of the box. We know the angle, theta. We know how far it's sliding down the ramp. That's going to be important because that's how far it's going to move. And that's part of our work equation. We also know mu sub k. That's given in the problem as well. The equation for work that we know is F dot D. We talked about this in class. F dot D means it's the magnitude of F times the magnitude of D times the cosine, the angle between them. I think a good place to start this, actually, it would be to rotate our coordinate system like this. So the way we're looking at this, the normal force, F sub n, and the curator's force and the kinetic friction are all on the xy planes, the xy axes. So the frictional force is in the negative x direction. The curator force is in the negative x direction. The normal force is in the positive y direction. The only one that's kind of at an angle, there's only one now that's at an angle, it's going to be the gravitational force. So the gravitational force is going to have a y component, Fgy, and an x component, Fgx. And since I rotated, it was here, and force gravity was straight down, I'm rotating it so that it's flat, which means that I have rotated the force of gravity at an angle of theta. So this right here is going to be my theta. And this bottom part of the right triangle is Fgx. Okay, so one of these is actually pretty obvious. The cosine of 90 degrees is 0. So any forces that are perpendicular to the movement, there's not going to be any work done. So one of those forces isn't doing any work. It's the one that's at 90 degrees from the displacement. That's going to be the normal force. So it's okay that that one wasn't included on my screen capture because it's not going to actually be doing any work at all. It's exactly perpendicular to the displacement. So F times D times the cosine of 90 is 0. The gravitational force. Want to start with that one? We can do that. Which component of gravitation is going to be doing work? Not the one that's in the y direction because it's perpendicular to the motion. So that won't be doing any work. It's only going to be the x component. So to find the work done by gravity, work from gravity is going to equal F times, sorry. F times D times the cosine of theta. Now it's working. Okay, good. The pencil is working. The F is going to be F, G, and the x direction. The distance is given in the problem, the displacement is 4 meters. And the angle is 0, and the cosine of 0 is 1. So it's just going to be f sub x, fg sub x times d, which is 4. How do we find the x component? Well, this right here is the x component. That is the opposite side of the triangle, so we're going to use a sine function to find that leg of that triangle. All right, so you're going to have to do that on your own, but that's how you do it. How about friction? How do we find the frictional force? Well, we know frictional force, F sub k, is going to equal mu sub k times F sub n. Awesome. We're given mu sub k. That's given in the problem, but we don't know F sub n. We have to figure that out. Well, looking at my diagram, I have a downward force and an upward force, and it's not accelerating up and down. Acceleration is 0. So the downward force has to equal the upward force. So F sub n is going to equal Fg in the y direction. How do we find Fg in the y direction? Well, that's going to be this leg of the triangle. And that's the adjacent to the angle theta. So you're going to have to use your cosine trig function to find that. And that's going to be the normal force. Once you have the normal force, you plug it in there, you can find the force of kinetic friction. So the work done by friction, is going to equal the force of kinetic friction times the displacement times the cosine of the angle between them. Cosine of the angle between them is not the green theta. The displacement is down to the right, down the ramp to the right. Frictional force is to the left, up the ramp. So they're exactly 180 degrees apart from each other. So that theta in this part is going to be 180 degrees. Cosine of 180 is negative 1. So negative work is being done. And that kind of makes sense. It's a force in the opposite direction of the displacement. So yeah, the work is going in the opposite way. Lastly, the force the curator is going to apply is going to be doing the work. Again, it's going to be 180 degrees, so that cosine theta term is going to become a negative 1. We have to figure out how much force the curator is applying. The key here is that the net force is 0 because the acceleration is 0. So in the x direction, F net equals m times a, so F net equals 0, which means the stuff going in the positive direction is going to equal the stuff going in the negative direction. So the force in the positive direction is Fgx. And that's going to equal the force in the negative direction, which is F of the curator plus F of kinetic friction. We figured out F from kinetic friction up here. And we figured out F sub x in our first part up here. The only thing we don't know is force of the curator. So we can solve that equation with force of the curator. It's going to be Fgx minus Fk. Once we have that, we can find the work done by the curator equals F the curator. My pencil's not really working very well on the corner of this page. F of the curator times the distance moved times the cosine of the angle between them. And in this case, it's going to be 180 degrees. All right, that's how you set up that problem.